So last time we derived an expression for the path integral representation of the propagator. Well, the word derive is not really a good word because it would, a more appropriate way of saying it would be that last time we invented an expression, a path integral expression for the propagator, inspired by Dirac and first, invented by Feynman. So what was it? It was that, the propagator, which is k, and so it's a function of x and tn, and x1 and t1, and it's defined in the Heisenberg representation, Heisenberg picture, by the inner product of the position eigenbases at time tn and time t1. So this is in the Heisenberg. And in Schrodinger, this is the same thing as, say, xn, the time evolution operator, going from t1 to tn at x1. This is in the Schrodinger representation. And, Feynman is telling us that this is equal to, a path integral where the measure of this integral, each element in this measure is a path, but that path starts from x1 at time 1 and ends at x and at time tn. And each path is weighted by a phase factor, which is exponential to the power I over h times the action, and the action is the integral of the Lagrangian from the time t1 to tn, where the integrand is the classical Lagrangian, which is a function of x and x dot dx, where we are saying that this classical Lagrangian is being evaluated for each path. So what does it mean, this formula? What this formula means is that, suppose that we start at some time. So this time is t1, and this is the x direction. And over here, I have the time tn. And suppose you start, your particle starts at some point, which is, say, x1, and ends up in the future at a different point, say, xn. And then what the Feynman path integral is telling us is that what we should do is that we should consider, even if it's not practically possible to do the calculation, all paths joining these two space-time points. Okay? And these paths don't have to be, they don't have to be smooth. They can be jagged, meaning that they don't have to be differentiable. And so for each of these paths, what we have to do is that we have to calculate what the Lagrangian function is on each point on this path, right? And then we integrate this from the initial time to the final time. So for each of these paths, I get a value of the action, and then I take the exponential of that action with this prefactor, so I get a phase. And then I add all these contributions, okay? So this was the Feynman path integral. And we also saw that in the limit in which h bar goes to 0, which is the classical limit. Let me just be, this is the classical limit. In this limit, what happens is that because a slight variation of the path causes this phase factor to change very, very rapidly and randomly, that most of the contributions from all these paths will be 0 because they will cancel each other out. The paths that will not cancel each other out is the path that the classical particle takes, which suppose is the one that I'm denoting by red. And that's because if I now vary the path of the classical particle, the action will be stationary, so that all the neighboring paths, so there is suppose a thin sort of a thin tubular region around this classical path. It's very, very small. It's infinitesimally, but this region contains all the paths which are infinitesimal variation of the path of the classical particle. And for each of these paths, the action is the same as the action of the path that the classical particle takes. And therefore, all their phases would be the same. And therefore, in this integral, they would constructively interfere. And therefore, in the classical limit, these are the paths which will contribute. Therefore, the h equals to 0 limit does give us classical mechanics. Okay, so this is a very blitz review of what we did last time. Okay, so this view of the path integral was formulated inspired by a comment from Dirac, and then Feynman added some assumptions such as the superposition principle, the associativity of the propagator, and a few other things. But you can show that this is exactly equivalent to the Schrodinger equation. So you can actually derive the Schrodinger equation from the path integral formulation. Okay, and that is what we're going to do next. Okay.